our course is about homological algebra. We will start from ordinary algebra, maybe recalling about algebra. Did you have some algebraic courses? Lie algebras. What about commutative algebra? Okay, no, maybe then let's start about some basic facts. No, do you know what's a ring? Yeah. Ring, it's a set with addition and multiplication, okay? We have addition, it's abelian group with respect to addition, yes? And multiplication, and we will assume that our rings our ring has unit and it has associative multiplication. But okay, of course, not necessarily commutative ring, okay? Okay? Not necessarily commutative. It's distributive law and so on. Okay. No, for example, any field is a ring, okay? Do you know what's field? Field is a ring where any non-zero element is invertible and commutative, of course, okay? Commutative ring, and any non-zero element is invertible. Something like matrices of some square matrices over some ring is again a ring, and so on. The second the basic object or subject of our study, it's a module, okay? What? Question? Do you know what the module is? Right or left module of a ring, okay? No, it's some set which has addition, so it's abelian group. And we have multiplication by scalars or by elements of some ground ring. We say that M is, for example, left R module if we have addition and multiplication by elements of R. No, in such a way so that we have distributive law. Okay. And associativity law. If we have multiplication in the ring and then we multiply this on the element of module, we obtain the same thing as if we multiply by the right one and then by the left one. Of course, if we have unit in our ring, as we will always assume, then we assume that unit x by multiplication by unit is do nothing, does nothing. Okay, it's left module. Right module, it means that we have multiplication from the right with the same distributive property, but associative law, this property, associative property, is this way. No, in obvious manner. Yes. Okay. No. Of course, no. It's no. You can write this from the left, but no. Then it's another property. Yes. You see that it's different property. If I write it from the left, then it's kind of this thing. Yes. It's not the same property. No, so it's maybe a little bit more natural write it from the right. Okay, so we have some fixed ring, and then we can say what is the left or right modules over this ring. Now, for example, any abelian group is module over Z, because if you have addition, addition and inverse elements with respect to addition, you already can multiply by integer numbers, okay? Because if you have integer numbers, of course, in any abelian group, it's abelian group, you know what is Ka with these properties. It's the left, right module. Yes, and of course, if your ring is commutative, then there is no difference between left and right modules. Because if you have, because if it's commutative, then this property is the same property. So if your ring is commutative, then there is no difference between left and right modules. But if not commutative, of course, it's very different. Okay? no, modules over fields, it's a vector space, and so on. Okay. Oh, and for example, if you have, if you have module, you can consider submodules. It's a abelian subgroup which is closed with respect to multiplication by scalars. Okay. From the left or from the right, it's maybe no. If you have left module, it's left submodules, and so on. If you have right modules, it's right submodules. Okay. For example, if you have ring itself, it's left or right module over itself, and then submodule of this ring of this module called ideal, left or right ideal. It's just submodule in the ring itself. It's some abelian subgroup which is closed with respect to multiplication by elements of all your ring. Okay, the whole ring. Well, okay. Yeah, also, you have if you have module and submodule, you can consider quotient module. Okay. If you have, for example, you have left module and left submodule, you can consider quotient is the left submodule. Do you know what the quotient is? Okay. It's quotient is a abelian group, and you can correctly define multiplication by scalars on this quotient as a abelian group. No, for example, if you have ideal in your left ideal, for example, in your ring, you can obtain left module, a quotient module. No, so for example, if you have two modules, the map between them, it's called module map or R-linear map. If for example, if it's left module, then something like this. Okay, for any elements R from your ring and M from M. Okay, if you have such R module map, then you can consider its kernel. It's of course submodule, left submodule, for example. You can consider image. It's submodule in N. And you can consider so-called co-kernel. Do you know what co-kernel is? It's quotient by image. Now, for example, F is injective, also called monomorphism, if kernel is 0. Okay, and F is surjective, so-called epimorphism. If image is all module, and it's equivalent to say that co-kernel is 0. Co-kernel is 0, it's surjective. 0 if it's surjective or epimorphism, epi. And this is 0, it's equivalent to say that F is mono or injective. Okay. You can say you can ask what is a co-image? Co-image is quotient by kernel, but maybe you know from algebra that quotient by kernel is isomorphic to image. So co-image is the same thing as image. It's algebraic fact. Okay. So we don't we can do not use any some different name for this object. Okay. Okay. No, and maybe the most important thing in homomorphic algebra is exactness of sequence of homomorphisms. If you have two maps, of modules, yes, then we say that this sequence, and it may be some sequence to right and to left, and we say that this sequence is exact in this place. This means that kernel of G equals image of F. In particular, composition is 0 because image contains in kernel. But no, it's more. It's как-то it's more accurate statement. It says that image is exactly the kernel. Okay. Okay. For example.
Here is like a long exact sequence. Right?
What?
We define like a long exact sequence.
No, I say that it's just if you have two composable morphisms, you can say what is exact in this place. And so if you have some morphisms, you can say what is exact in any place. If you have long sequence, you say that all sequence is exact if it's exact in all places. Okay. Now, for example, something like if you have some morphism, you have exact sequence. For example, if you have if this sequence exact, this means that kernel of f is exactly 0, so f is monomorphism. For example, if this exact, this sequence is exact in this place, we can say, no, if we have exact, if we have sequence, we can say that it's exact only in internal place, not in boundaries. Okay, so this sequence is exact in this place. This means that f is epimorphism. Yes. The most important case is exact sequence of this form, exact in this, and these places. No, such exact sequences called short exact sequences. Mm-hmm. This means that M is submodule of N to K is surjective homomorphism, epimorphism, and image of M is exactly the kernel of this surjective homomorphism. Mm-hmm. Some constructions with modules. If you have two modules, for example, yes, for example, M is. Do you know what is tensor product of abelian groups is?
So pairs of A1 and 2.
Tensor product of two abelian groups. Do you know what is it? No. Okay. No. Okay. No. Then if M is right R module and N is left R module, then you can define the tensor product. No, do you know what the tensor product of abelian groups or not? Or no? Okay. No, then it's kind of no, it's abelian group. It's abelian group. It's not R module in general. It's abelian group generated by all sums, if you want formal sums, of tensor products, formal pairs, okay, of elements from M, elements from N. It's abelian group of formal sums. Modulo following relations. That if you have something like this, of course, for another place also. No, if you stay here, then you obtain the so-called tensor product of AZ, tensor product of as abelian groups. But if you have R model structures from the right here and from the left here, then you can add some another relation, is relation of this form. So for any element M from M, and from N, and R from R. So you can move this factor from left to the right. So you need that M is left R module, right R module, and N is left R module. Do you understand what this means? That if you have for formally saying you have this abelian group and you have abelian subgroup generated by differences of these elements. Okay. Okay. If R is commutative, it's important case, then this thing has a natural R module structure. Then this thing is R module. No, left or right, it's not important if R is commutative. No, by the following rule. No, because if R is commutative, then all my modules are left and right in the same time. So I can, for example, assume that they are left. So, and this is the same thing as this and so on. And you can check that this is correctly defined R module structure. no, what exercise? You can think about the following question: why this does not work for not commutative ring? What if R is not commutative? Why this rule does not work? And it's one point. And another point: if R is not commutative, why in this definition, for example, I can't use two left R modules and use relation of, no, for example, of this form. What if I want something like this? Why it's bad? Bad idea. This does not work. What? No, it's more or less not formal exercise, but no, it has some answer. And dual construction, if you have two left modules or right modules, it's left or right at the same time now, then you can define, of course, homomorphism. It's the set of all R module maps. R module maps. R module homomorphisms. Homomorphisms. From M to N. And it's also abelian group. Just abelian, because, no, of course, if you have two homomorphisms, you can consider their sum, and it's again R module homomorphism. But you cannot define R module structure in general if R is not commutative. If R is commutative, again, then this is, of course, R module, no, with this natural definition. Rf, it's new homomorphism on some element. No, it's something like this, or it's the same time. It's the same thing because it's R module map. And again, you can think why this rule, why this definition does not work for not commutative ring. It's not. It does not work. Okay. It does not work for non-commutative ring. But for commutative ring, of course, we have this R module and this R modules. Okay. This for for commutative we have no difference between left and right. So of a commutative ring, for any two R modules, we have tensor product and home. Okay. No, and of course, something like a junction between them. I think we will check these exercises on seminars. Some of them. If you have M right R module N left and K also left, for example, then you can consider tensor product over some R. It's a tensor product, okay. And you can consider K. You can consider home. No, this is just abelian group. So if any R module is also abelian group. So you can consider K as a abelian group and consider home as abelian group over Z, over ring Z. No, and on the other hand, you can consider home. No, okay, home abelian groups from M to home R in K, for example. It's also abelian group, abelian group, abelian group. Yes. No, and this is isomorphic things. In general, for not commutative ring, there is natural isomorphisms of these abelian groups. And if R is commutative, then these things is all R modules. And so if R is commutative, we can replace ab for R. So we can consider R modules maps here and R modules maps here, and this is also isomorphism. Okay. Sorry. Okay, do you understand the exercise? Okay. No, it's so-called adjunction between tensor product functor and home functor. But maybe, no, I will try not to use term functors and categories. Because, okay, меня просили. Так, okay. No, it's important property. Maybe we will, no, sometimes it helps you, no, reduce some questions about tensor products to questions about homes and vice versa. No, you have some obvious properties, something like. Yeah?
Sorry, but the definition of this subindices have, sorry.
Oh, it's homes as abelian groups. No, if you want, it's homes as models over Z. Yes.
Okay.
No, it's just homes of abelian groups.
Okay.
Sorry. Yes. No, because if R is not commutative, this is just abelian group. And if you forgot your R model structure and consider K only as abelian groups, just as abelian groups, you have some home of as abelian groups. Okay, all abelian groups homomorphisms. No, yes, maybe Z, and if R is commutative, we can replace Z to R. Okay. Now, no, we have some obvious properties, also exercises, but it's kind of easy exercise. No, for example, if you consider direct sum of family of modules, what is it? No, it's just, no, if you have some family of indexes, then you consider sequences of elements of modules numbered by elements of this family, but such sequences which has only non-zero, only finite numbers of non-zero elements. Okay. So we can consider direct product. It's all sequences of elements numbered by some family index, index of family, family of indexes. Okay. And here is submodel generated. Contains only finite sequences which are non-zero only on finite numbers of indexes. Okay. I don't know, number of places. Okay, understand what I want to say? It's all sequences of elements, and this is all sequences of elements such that for all except of finite numbers are 0. Okay. No, if you have only finite numbers of models, this is the same thing. But if you have infinite numbers of models, this is the different models. Okay. No, so and we have some properties. So exercise is that, for example, you have direct sum of modules, and consider tensor product with something which is isomorphic to direct sum of tensor products, and on another side also, if you have home from direct sum to some module with the same as product of home from M alpha to N over R.
So what is this last sentence for all except?
No, it's all families, okay, all sequences of elements, yes. And this is such family, such sequences, such that for all except of finite numbers of these elements are 0. So you have only finite number of non-zero, and all other are 0. Okay. So for example, if you have countable many of modules, you can consider such sequences which has some elements on some places, but all except of finite numbers are 0. Okay. Я правильно использую слово except of? Мне кажется, да. То есть, ну, в принципе, понятно, что я имею в виду, да? Хорошо. Я просто не знаю, как это сказать нормально. В смысле, я даже не знаю, как это определить нормально. Ну, формально там через функции можно. Okay. And, okay? And if you have home from M to, it's direct sum, it's direct product. To direct product of modules, this is the same thing as also as direct products of home. No, this is exercises. No, it's kind of easy exercise. Easy It's so easy that, so maybe we will not check them on seminars. But maybe I will ask you them on exam. Another situation, more general situation. Maybe we have the following situation. We have some abelian group X, and we have two rings, R and S. And maybe you have left multiplication by the elements of R and right multiplication by the elements of S. So you have these things and these things, and you have this multiplication satisfies properties of left module structure, and this satisfies properties of right module structure. So this is left R module and right S module, and these two multiplications commute. So we have this associativity. You can multiply from the left and then from the right, or maybe in opposite order. From the right and then from the left. And you must obtain the same element. Understand the situation? This situation called that X is RSB module. So it's left module and right module, and these two actions commute. Two multiplication by scalars commute. For example, any ring, not necessarily commutative, is RB module over itself. No, because you have right multiplication in this ring. No, you have multiplication in the ring. You can consider it as right and as left, and you have ordinary associative law, because I assume that all my rings are associative. You do not need you don't need commutativity here. Okay. And then, if you have such situation, then for example, if you consider what you have RSB module, if you consider left S module, for example, M is left S module. Then you can consider tensor product over S. But it's just abelian group. But you also have left R module structure on X, and then this thing is itself has left R module structure by this obvious rule. So this is R left R module. No, and in the opposite order, if you have some right R module, this thing has right S module structure, inherited from B module structure of X. Okay. And for home also, and the same thing true for homes. For example, here. If you consider home from X to for example just 1 second. To left, if M is left R module, X is also left R module, and you can consider this thing. If X is only left R module, this is just abelian group. But if X is also RSB module, you can consider R. You can consider left. Left. This is left S module. Left S module with the following definition: F of X is F. So please check that this is important. Multiply here from the right inside of function to obtain left S module on the set of all functions. Please check this. It's exercise. No, there's also exercise to check that this is left module structure on tensor product, but it is more or less obvious. But this is maybe, if it's not obvious for you, please check this. This is left S module. If you have right S module on X from the left, then on home you obtain left S module. X is right S module, and home is then left S module. No, and On the other direction, if you have, of course, if you have home from to x, from left R module. Yes, this is left. No, yeah, yes, left. From left R module to x. Then this is right S module structure. Right S module structure by this definition. What, sorry. This element from x, and you can write a structure. This is right, okay. If you define your model structure from the target, you obtain the same direction. If you define your model structure from the domain, you obtain the opposite direction. Okay. This is kind of exercise, and of course you have the similar adjunction. If you consider here what x m n m x n r s r yes. Oh. M is left as module, and n is left R module. Left S, left R. No, this is RSB module. So this thing is also left R module. You have home. This is abelian group. It's an isomorphism of abelian groups. And if you have left S module, this is also left S module. So by these definitions, left S module. And you can consider the home of left S modules. This is abelian group, but these two abelian groups are isomorphic. No, this is kind of it's strict generalization of the previous one, because any for example any left R module is, for example, RZ B module, because you have always trivial Z multiplication on the right and on the left. So the previous one is the strict particular case of this one. If you consider one of these rings just Z without any additional information, and this is generalization for B module structure. Okay, so the previous the previous exercise is particular case of this one. Okay. And important particular case of this situation, where we can find B modules in nature. In the following situation, for example, you may ask what maybe B module is something unnatural, but it's kind of natural, in fact, because, for example, what if we have the following situation? We have homomorphism of rings, two rings, not commutative, maybe. Then, for example, S have RS and SR B module structures. If you have homomorphism of rings, then target has these B module structures. No. In what sense? No, because of course you can multiply two elements of S. So S has right or left S module structure. But what's the right? What the R module structure? No, it's the multiplication of the image of element of R by this F. For example, this structure it's R S prime is by S prime is just S prime. Okay, and this by definition it's FR S. You can multiply elements of S by elements of R by considering image of R by this homomorphism. Okay. So if you have ring homomorphisms, you can consider S as R module, because you can consider any scalar from R, consider its image, and then consider multiplication by this image. So if you have homomorphisms, then you obtain R module structure on this target ring. And in fact, you obtain B module structure on this ring, because you have multiplication from one side by images of these scalars, and from the another side by elements of S itself. Okay, and then we can use something like this in the following way. For example, if you have this ring, you have this functor, this operation, this map from R modules from S modules to R modules. If you have left S module, if I write a letter from the left, this is left module. This is right module. Okay. If you have left S modules, you can obtain from left S module left R module. How? No, if you have some left S module, you can consider this module itself, but what R module structure we can consider here? No, if you have some element of R and you need to multiply it by element of M, you use this idea. You can consider just image and then consider S module structure. No, so this is particular case. S is forgetful of R module structure of this is just this function on S as S module. Okay. This is R module. Okay. If you have some M module, you can consider it as R module via this homomorphism. No, it's called something like restriction of scalars, because if it's injection of subring, you just restrict your scalars on subring. You just consider a multiplication only by this subring. But it's not important that it is monomorphism, so you can consider any other homomorphism from any other ring and consider this restriction of scalars on this domain, okay? Via this homomorphism, okay? Mm-hmm. Okay. So we have this operation from S module to R modules. This is with this R module definition. And we have two operations in the opposite direction, from R modules to S modules. We have extension of scalars and co-extension of scalars. Yes. Extension of scalars. I will denote it by this. From R mod. No, it's ordinary extension of scalars. It's just if you have R module, left R module, you can consider S tensor over R. You consider S as right R module here via not via by this definition, by this definition. Okay. This bimodal structure right R module. But also S is itself left S module, and so this standard product is a left S module with the module structure inherited by from left S module structure on S itself. Okay. Now, if you have some this thing, you can of course multiply by this rule. Mm-hmm. So we obtain some operation from left R modules to left S modules. It's extension of scalar. If you have a real vector space and you consider complex numbers, you obtain extension of scalars of vector space. Okay, it's complexification. Okay. And you can consider another thing. Co-extension of scalars. It's extension of scalars. Extension of scalars. Extension of scalars. It's restriction of scalars. It's co-extension of scalars. Co-extension of scalars. Also from R module to S modules. If you have R module M, you can consider home from S to M over R. If M is left R module, you consider S as R as B module, left R module structure. You can consider this home, and again, because S is now right S module over itself, this thing has left S module structure. And so you obtain left S module. Okay, and again from this general isomorphism, you can obtain the following two isomorphisms. It's also exercise. Hom over R from M to restriction of scalars is isomorphic to hom over S from extension of scalars. N and hom R from extension to scalars, from extension to scalars to M isomorphic to S M N to coextension of scalars. Now here N is a S module, left S module, and M is left R module. Yes. No, in fact, these two isomorphisms is corollaries of this isomorphism. If you consider two different bimodal structure on S, RS bimodal structure on S and SR bimodal structure on S. Okay. And this is kind of useful thing because if you have two rings and you want to compare models over them, you can consider restriction like coextension, like an extension. You have some of these concepts. It's kind of useful. Maybe in some moment we will see this. Okay. Maybe in some moment we will see some generalization of this isomorphism, some spectral sequence.
So here this N and M are both left or right?
Left, for example, left. What if I write letter on the left, then it's left modus. But yes, maybe I will. Yes, left. They are left. They are both left or both right. Yes. For example, here I assume that they are left. Okay. No, because here I define something like this because so I need that M is left R module. Yes, because I need left multiplication here on this relation. I need a left R module structure. If I tensor module from the right, I need left. I need that R from the left here. So M is right R module. M is left R module, and S I consider as right R module here. By definition here. Okay. Now maybe about some start of homological things. Now maybe a little bit about linear algebra. Do you know what is free module? What is free module?
I mean, it has universal property.
What?
Like this. Why I need to write?
No, free. No. Okay.
It's formal combinations.
No, yes. What M is free. For example, left R module. If M is isomorphic to direct sum of copies of R itself, okay, it's equivalent to say that M has R bases. So it's set of elements of M such that any element uniquely can be expressed as finite sum of these elements with coefficients from your ring. And so this finite sum corresponds to that this is direct sum. This finite numbers of coefficients of these expressions. Okay, it's free module. No, if it's not obvious, also you can check that this is the same thing. This is direct sum, and this is has basis. Okay. No, unique expression. I mean, yes. Exists some elements. Okay, but what we can say about cardinality of bases, cardinality of these summands. What you could say about cardinality of bases? What do you know about cardinality of bases of free modules? Do you know something about cardinality of bases? Maybe from linear algebra. What? No, cardinality, yes, it's what?
Countable.
No, it's not important. It's some cardinality. But what you can say? If you have two bases, what you can say about cardinality of them? What about number of elements in two bases? Same. Because we know this from linear algebra. Over field, if you have vector space, it's not. In fact, it's not important. Countable, uncountable, finite or not finite, infinite elements in bases. In fact, it's general theory. Maybe you did not prove it for infinite bases, but it's true that if you have vector space over field, it's model over field. And if you have two bases, then you can construct bijection between them. What? If you have R is commutative ring and M is free R module, then this is also true. Any two bases are bijection. No, why? Because it's some idea of proof. If you have commutative ring, then it's also general fact. It follows from the same thing that implies that any basis of vector spaces have the same cardinality. It's some kind of Zorn lemma or axiom of choice. But it's true that if you have commutative ring, there exists maximal ideal. It's ideal. It's some R submodule. No, R is commutative, so it's not important left or right. Such that no, it does not contain any greater ideal. Okay, it's maximal ideal. So if you have some ideal such that it if you have some ideal in R such that I is not R itself, then no, sorry, stop. It's not important. So, no, yes, it no. If you have some ideal such that greater than M, then it's only R itself, something like this. It's what does it mean that it's maximal ideal? So it's algebraic fact that such things exists. And if we consider this maximal ideal, you can consider quotient by this ideal. Okay, so it's some quotient module. It's some module over R. Very easy. It's not easy that maximal ideals exist, but it's very easy exercise from algebra. It's really easy. That quotient by maximal ideal is a field. That thing is a field. It's commutative, and only I think that you need to check that. No, you need to check. No, if you have ideal and quotient by ideal, it's also ring. You have multiplication, and you need to check that any non-zero element is invertible here. It's because M is maximal. If you can find some not invertible element, you can construct greater ideal. In fact. Okay, what we obtain? We have some quotient map. So if we have free module over R, we can consider its tensor product over R on this thing. No, because we have ring homomorphism, this thing is field, but this is R module itself via this homomorphism, and we can consider this is Rm module. If M is free, then M is isomorphic to direct sum of R itself. So here I have tensor product this thing over R of direct sum. As I said before, direct sum and tensor product compute, so I have it's isomorphic to direct sum of these tensor products. Oh yes, it's very important very important exercise here. If you have tensor product with R itself, it's always isomorphic to M. It's not important here that R is commutative. And if you consider home from R to M, it's also isomorphic to M. If you consider home from M to R, it's not isomorphic to M, it's called dual module, and maybe we will use them later. But here it's isomorphic. So here, no, it's easy exercise. And so here, this is the same thing as this module, so it's direct sum of these modules. But this thing is a field. And no, we obtain isomorphism of R modules, but no, and and hence this is isomorphism of R modulo M modules. But R modulo M is a field, so it's isomorphism of vector spaces over this field. But we know this. We know that for vector spaces over fields, the dimension is invariant. So no, if I have two bases, I obtain two expressions as direct sums, and if I have a different number of summands, then I see these different numbers in dimension of this vector space over field, and this is not possible. Okay? No, on the other side, if I have M is isomorphic to another direct sum, over another set, then I obtain the same isomorphism, this thing. But this is field and this is vector space. This is just dimension of this vector space over this field, and so these two numbers must coincide. Okay. So over any commutative ring, this number of summands, and so this is number of elements of any basis, is invariant of isomorphism. It depends only on M, so it's correctly defined number. It's interesting that it's absolutely not true for not commutative rings. Now, for example, it's exercise for you. It's not, maybe it's not very easy now, but it's a fun exercise. No, there exists ring, not commutative, of course, such that R itself is isomorphic to R plus R as R modulus, as, for example, left R modulus. So over not commutative rings, even finally, there exist modules such that one-dimensional and two-dimensional at the same time. And they are free, of course. So commutativity here is a crucial thing. So in fact, this is not true that we have some dimension of free module in general situation. We have not, in fact. Okay, it's exercise. Maybe we will discuss this example on seminars. Okay, so we can say about dimension of free modules only over commutative rings. Okay. No, it's maybe because this step also not true, because we have maybe some non-commutative rings which has no two-sided ideals itself. Not even maximal, but no two-sided ideals ever. No, maybe such some these webs. No, they exist. There exist some rings without two-sided ideals. No, except of 0 and R itself. Non-trivial two-sided ideals. You have left ideals, right ideals, but if you need two-sided, because if you need something like field, you need two-sided ideal. Maybe they do not exist in some rings, and so this proof does not work. But in fact, this result just false. Just false here. Okay. Motivation for homological algebra, and then we will start homological algebra. It is kind of end of ordinary algebra. Now we maybe need to start homological algebra. The main motivation for homological algebra is the following. The following result. But consider short exact sequence of modules. Left or right? Left. It's short exact sequence of modules over some ring. And consider another module, A. Then, it's obvious that if I have map of modules But is it obvious that if I have map of modules, for example here, then if I consider, for example, home from A to M, home from A to N, and home from A to K, then I have induced homomorphism, yes? Do you agree that I have induced homomorphism? In what direction?
Right.
From left to right, yes? No, yes. No, it's obvious. It's obvious definition. I do not give you a definition, but it's obvious. Yes, you have obvious induced homomorphism, and zeros here and zeros here. But now, what about exactness of this sequence? Now, for example, what if I write 0 here? For example, the sequence is exact in this place. So this homomorphism is epimorphism. Yes, правильно говорю? Нет, я говорю неправильно. No, it's not true. No, it's exact here. Well, it's monomorphism here. No, this is obvious. Because you have injection here, then on homomorphism it's also injection. Because if you have homomorphism to M, and then you consider it as homomorphism in N, no, if two homomorphisms coincide as homomorphism in N, but M is submodule, then they coincide as homomorphism to M, okay? To submodule. It's monomorphism. Okay? No, because here you have two homomorphisms to M. You consider this homomorphism to M as homomorphism to larger module N. And if you consider they as homomorphism to larger module, they coincide, but they have как называется, забыл, values in little module. And so if they coincide as with values in greater module, they coincide as homomorphism in little module, okay? Я запутал вас своими словами, да? Ну, is it obvious that this is injective map? If you have two homomorphisms from A to M, you consider them as homomorphism to N. And if you consider them as homomorphism to N, they coincide. Then they, of course, coincide as homomorphism to M, okay? Because they take values in little module. Okay, so this is injective. And so this sequence is exact in this place. In fact, this sequence is also exact in this place. So this sequence is exact. Image of this map is exactly the kernel of this map. This is exercise. It's important exercise. We will check this on Sumeras.
0 on the right.
Of course not. And this is where homological algebra starts. Because if we have 0 here, it would not, как это сказать, тогда бы не было homological algebra, как это сказать в правильном времени.
Okay,
They wouldn't be homological algebra itself, yes. But there is not, this map is not epimorphism. No, it's because, what does it mean? It means that if you have epimorphism, surjective map, and you have some homomorphism to K, you need that there exists some map to N such that this diagram commutes. You need some lifting of this map. But not for all modules this is possible to obtain to construct this map. This map maybe not exist. So this map is not always homomorphism, and you have some continuation of the sequence, and this is where homological algebra and derived functors arise. This is homological algebra. But please check, and maybe we will check this on seminars, that this homological algebra starts here, not here. This is exact here. Please check this. Okay. On the opposite direction, if you consider home to A, yes, you have home. No, then you have induced homomorphism in the opposite direction, yes? You have from A, M, N, A, and home. Yes, sorry, I don't use R here, but no, because it's R model, so yeah, of course I'm about R model maps. Then it's also exact from the left. It's exact on this place, not this place. Again, this map is injective because, because what does it mean? That if you have n surjective map to k, and then you map k to A, if you have two maps here, and they coincide on k. No. And you consider compositions, and these compositions coincide on n. But because of this map is surjective, if these two maps coincide on n, then they coincide on k, okay? If I, for example, if this is P, this is P. If I have two maps here, this is P star F, P star J, it's just composition, yes? F, P, no, sorry. No, yes, it's FP and GP. Yes. If this composition coincides, and this map is surjective, then this map coincides also, okay? It's obvious. If this composition coincide and this is surjective, then this maps coincide on K, because it's surjective. Maybe if it's not surjective, maybe they do not coincide on beyond the image of n. But because n is surjective, if this composition coincide on n, then they coincide on image. No, then they coincide on image, and the image is K itself, okay? If you have two maps, and this composition coincide, then this is equivalent to say that these maps coincide on the image of n, okay? And if image is K itself, then they coincide. And this is exactly what I say. If I say that I have two maps here, they coincide here, then they coincide here. This means that this map is injective, okay? No, and also extract that this sequence exact in this place also. And here this is not exact, and so homological algebra starts here too. No, in fact, this is the same homological algebra. No, and for tensor product also. For tensor product, now here I consider A is the same model. If this is left model, then A is left model. Now, if this is left model, let A is right model or vice versa. And I can consider tensor product with A, something like, for example, in this direction. It's not important. Then, of course, I also have induced homomorphisms. And in fact, now it's obvious if I can consider any element of K as image of n, then any tensor Ka is image of some tensor Na. And then any sum of them is the image of any sum of them. And then tensor product itself is the image of this. So this is surjective, it's obvious. Also, it's exact here, but not exact here, so we have also homological algebra here. Its motivation, what we need to do to obtain something, some exact sequence, some continuation of this exact sequence to the left here and to the right here. And this is some motivation of homological algebra considerations. Okay, please, try to check this. For at least, if it's not obvious with tensor product, maybe at least for home, where it's extremely here. It's just homomorphisms, just maps, and please check exactness of the sequence in these places. It's important because it's the first step to homological algebra. Okay. But okay. But now let's consider such good modules, maybe for which this sequence exact with zeros here. What does it mean? What we need to be okay. But for example, what I need to say about A such that for any exact sequence of this sort, this exact sequence with 0 here is exact. So such that for any this thing, my induced exact sequence is exact, for which A is this true. No, what does it mean? I know that this sequence is exact here and exact here always. So all what I need is exact in this place. So all what I need is surjectivity of this map. And as we see before, surjectivity of this map means that if I have surjective map here, and I have a map from A to K, this must exist some map from A to N. Okay? It's what I need. If it's true, then this sequence is exact on this last place. And vice versa. If this sequence is exact in this place, it's equivalent to say of this property. Okay? Because for any surjective map, I can consider kernel, and this is in fact consider short exact sequence of this form. This is equivalent to say. So this is the property of my modules. Okay, left A module is called projective. If for any surjective homomorphism of modules and any map for any P surjective, any F, there exists G such that composition is F. Is the definition of projective modules. Maybe I would denote them by P, but okay, уже поздно. Now, why projective modules exist? Why does they exist? Why do they exist?
Because the sequence is exact.
No, it's not exact in general. In general, it's not exact. I consider just such modules such that this sequence is exact. Maybe such module doesn't exist. Why does these models exist? Maybe there are no such modules. Free modules. No, for example, zero module satisfies this property. But okay, any free module is projective. So it's free projective. No, it's obvious because if you have surjection, you have free module F, free module, and you have map. Now consider some basis here. Basis. Consider its images of basis, some elements K alpha. This is surjective. You can consider some pre-images, some pre-image, some elements n alpha such that they goes to K alpha, and then just define this map. Sends basis to n alpha, and if a free module has such properties that homomorphism from free module to any other module is the same thing as that function on basis. If you define values on basis, then you can uniquely extend this to the homomorphism from free module. Yes, okay. Hom from F to something to n is the same thing as alpha to something. If you have some functions on basis, then you can uniquely extend this to the homomorphism from free module. No, by uniquely extension to linear combinations of basis with R coefficients. And so we can define these values on basis as some pre-images of these values, and then consider a unique map. Of course, because you can consider some other pre-images, this you can obtain other definition of this map. So this map is not unique because you have maybe many pre-images of these maps of these elements. But but this map exists.
I have a question.
Mm-hmm.
Do we require in the definition of projective model that the diagram commutes?
Of course.
Yes. So the question is, why do we need for this to be commutative? Because maybe I don't understand something, but if we want for that map, home maps between.
No, because
we-
in this induced map, if you have map A from N, then its image is just composition, and you need that. No, this composition must be some elements here. No, you need to. No, if you have some G here, you can find some homomorphism here such that it must goes to this element. This is G. No, G. So I think it's G, F. F is A from K. You find in G, and this image is just composition. So you need that this composition must be equal to F.
Okay.
By definition, because you find a pre-image, the strictly pre-image.
That map, you mean that map between home is just P star?
No, I ask, is it obvious what induced homomorphism? I did not define it, but yes, of course, it's composition. It's composition. So, okay, this is composition from the right. On the other direction, it's composition from the left. Yes, of course. Of course. No, what other it must be? Okay. What other it can be? Okay. So is it obvious that free models are projective? You can define this lifting by как-то choosing values on basis, and you can choose values for basis because because this map is surjective, because you have some choice of pre-images of these elements. Okay. No, okay. Bunch of exercises, because all easy properties we will consider on seminars. Important properties of projective modules. First one, of course, in fact, projective modules, they maybe is not the same as free models, but they are not so far from so distant from free models, because okay, let P is projective if and only if it's a direct summand of free model. If and only if there exists some model U such that P plus U is free. No, then U is also projective. For example, do you know what does it mean, principal ideal domain? Okay. Now, for example, this means that for abelian groups over Z, abelian Z modules, it's abelian groups. For abelian groups, maybe you know that direct summand of free model is free abelian group, and direct summand free abelian group is also free. Maybe you know this. Okay, this is true. For abelian groups, direct summand of free abelian group is free. It's not true for all rings or even commutative, but for good rings, for example, for integers, this is true. The direct summand of free model free abelian group is free. So for Z model from this exercise, you obtain that for Z projectives is the same thing as Z free abelian group. So over Z, only projective projective models are only free models, only free abelian groups. But you need to check this property. There is also fun thing here from this property. For example, let me know this, and then it's sometimes called swindle. I don't know, something like this. Okay, let P plus U is free. It's F. Now then consider something like this: P plus U plus P plus U plus P, etc. On the one hand, on the one side, it's sum of F plus F plus F, so it's some direct sum of free modules, so it's free. Okay? Direct sum of free module is free module. But on the other side, it's sum of p plus u plus p plus u plus p plus u plus p, but u plus p is f. So it's isomorphic, no, it's equal isomorphic to p plus, no, the same thing, the same free model. This is kind of plus this f, also free. So in fact, for any projective model, there exists some free module such that this model plus this free model is isomorphic to this free model itself. But here, no, it's crucial thing that you obtain countable sums, so infinite sums. So for example, if you restrict your attention to some calls to finitely dimensional or finitely generated free models, this is not true, of course. But for all free models, this is true that projective model is a for any projective P, there exists free f such that P plus f is just f. Is this tricky consequences of this property? But this is not true for finitely generated. Maybe sometimes later we will consider some restrictions on models and some abstractions to say that this is maybe, no, sometimes it exists a finitely generated free model with this property, but it's not usually. Okay. No, FG is finitely generated. It's a free model of with finite basis, something like this. No, so here we see that this model is obviously not finitely dimensional. It's countable sum. Okay. So it's crucial that this is not finitely generated. For finitely generated, it's not true, and there is the whole theory here about finitely generated things. Maybe we will discuss it later. Okay. No, yeah, this is the first property. So projective models is always direct summands of free models. Some easy properties. No, for example, direct sum of projectives is projective in direct summand. So direct sum of modules is projective if and only if each summand is projective. It's also exercise. It's also exercise. No, it's easy exercise. Okay. Another property. No, maybe okay. Maybe it's enough properties. No, yes, it's another property. Maybe something like if P is projective, then extension of scalars is projective. It's R projective. Then extension of scalars by some, okay, we have some homomorphism, and this is extension of scalars. By definition something like this, then this is S projective. So projectivity, extension of scalars respect projectivity. No, the opposite is not true. Maybe you can extend scalars that you obtain projective model, but this doesn't imply that it was projective itself. But in this direction is true. It's not very. It's easier if you use some adjunct homomorphism between home and the product, which I wrote before. Okay. Dual situation. What modules have the same property but for another induced homomorphism sequence? If we have, this thing, and I consider map to something, to some module, then I have A. Here also is composition, but from the other side. What I need from module A to say that this map is surjective. Yes. what does it mean? This means that I have some injection. And I have some map from M to A, and I want that there exists an extension of this map to N for any overmodule, of course, it's very strong property of A. I want that for any submodule, if I define map from submodule to M to A, then there exists extension on the whole module for any submodule pair. It's very strong property of A. In this situation, this always will be surjection, and this sequence will be short exact sequence. Now, such modules called injective. A is injective if for any injection, if I have map from some module to A, then there exists extension to the whole module to it. It's it seems strong property, yes? And so, and in fact, injective modules kind of a little bit less obvious things. So maybe it's not, here it's not obvious why these injective modules exist, except of 0. Now, for example, of a field, any module is free, it's vector space. And of a field, any free modules is injective and projective. Okay, for vector spaces, maybe from linear algebra, you know that these things are exact. Okay, but what about general ring? For example, what about maybe abelian groups? What is injective Z modules, то есть без abelian groups? For example, free abelian groups, Z itself, is not injective. Why? Now, please give me some example of submodule and map to Z such that it does not there does not exist extension on the whole module, for example. Maybe there are no injective modules of Z except of 0. What Z is injective or not? Due to our schedule is similar, so I ask you. No, maybe you can give me some example of some abelian subgroup and some homomorphism to Z, such as there are no extension here. Maybe, okay, maybe here. Huh?
It must be free, right? So we are looking for free abelian.
Yes, it's all Z. It's a hint. It's a yes. You need to define this homomorphism injective and this homomorphism such that there is no extension here.
Maybe multiplication by 2 and by 3.
No, by 2 and by 3, and maybe by unit here, by identity here, and something like this. Yes, okay. Mm-hmm. If you have identity here, you can't extend multiplication by 2 because if you need to define image of unit here, but unit here is not in the image, and yes, it must be something like 1/2 here, yes, because unit here goes to unit here and goes to 2 here, so unit must go to something like 2x is unit, and there are no such element in Z. Okay. Mm-hmm. But if you have this map, this means that identity is divided by 2. It's not true for Z. Okay. The identity homomorphism is not divided by 2. There are no homomorphisms such that 2 of it is identity, because this identity holds for example, for unit is not true, or for any odd element. Okay. Okay, but here, for example, no, what kind of abstraction we see here? It's kind of divisibility of elements. In fact, this is the only abstraction. But let's check this proposition. Abelian group A is Z injective if and only if A is divisible group. Divisible group, this means that for any A from A and for any non-zero integer number, there exists X such that A is an X. You can divide any element by any integer number, not necessarily uniquely. For example, you can divide it not uniquely, and this means that there is torsion. So, for example of such group is Q, of course, and any rational vector space, of course. In this abelian group, you can divide uniquely. But for example, you can consider something like Q modulo Z. It's rational. It's rational points on circle, for example. On it's rationals modulo integers. It's rationals on interval 1, 0 modulo integers. Okay, because if you have two elements here, to sum them, you sum them here and then consider here something like this. Okay, okay. Understand what does it mean? It's quotient abelian group. Okay, and it's also divisible because you can divide it. For any element here, you can divide 1/2 and 1/3, but not uniquely in general. In fact, no. For example, no. You have in fact you have many choices of divisible elements in this group. Okay, it's not unique dividing here, but it's possible. So this is also injective abelian group. Okay, let's have a break, and then we prove this property, this proposition.